In our last video, we saw some empirical evidence for identifying acids and bases. What we're going to do in this video is put that evidence into a theory of acids and bases. Specifically, we're going to be looking at what is called the Arrhenius Theory. And the Arrhenius Theory is named after a scientist, and I'm going to try to spell his name correctly here, called Svante Arrhenius. And what Svante Arrhenius noticed, just like what we saw in the last video, was that acids and bases conduct electricity. So how do acids and bases conduct electricity? Well, this is what we can put together from this. So hydrochloric acid in this particular beaker, let's say I've got a certain concentration of hydrochloric acid, and it has some electrodes inside the beaker that are connected to a battery and a light bulb. This is what we would call a conductivity apparatus, and you've used these before in a lab. This is a conductivity apparatus, and I've just done a very crude sketch of one, but you can imagine it kind of looks something like this. It's got a battery, some wires hooked up to a light bulb, and then it's got two electrodes that you would stick in the solution, and if it conducts electricity, the light bulb will flash because it allows the flow of electrons through its circuit. All right, so what do we notice in our last little video where I demonstrated this? Well, when I stick these electrodes into some hydrochloric acid, it allows for the flow of electrons. Okay, allows for the flow of electrons, and the light bulb blinks on. So that tells me that it's conducting electricity. Now, why does it conduct electricity? Well, in order for solutions to conduct electricity, there needs to be ions, dissolved ions in this solution. As you know, ions are charged particles. They can either be charged atoms or charged molecules. The thing that they need to have are charged particles, either atoms or molecules, in the solution. So because hydrochloric acid conducts electricity, this tells us that the hydrogen chloride dissolved in water must somehow dissociate into hydrogen ions and chloride ions. And this is actually what Svante Arrhenius proposed. He proposed that hydrochloric acid, when it's dissolved in water, dissociates into hydrogen ions and chloride ions. And once it does this, it's these ions here that conduct electricity. Which is why we see the little light bulb flashing. So this is his proposal, his theory here. Okay, this substance that's in the water must dissociate to form hydrogen ions and chloride ions. And he used the word dissociate, but you'll perhaps remember in an earlier video I talked about the difference between dissociation and ionization. He used the word dissociation at the time, and that's because ionization just wasn't used. Now we know this as, this whole process here is called ionization, but the end result is similar in that I'm producing ions in solution, and ions in solution will conduct electricity. So here is the proposal. This is what we see. We see hydrogen ions and chloride ions produced in this solution. All right, so that's why we see the light bulb flash with hydrochloric acid. And I could put in another strong acid here, like sulfuric acid or nitric acid or perchloric acid. Any strong acid here, I can put these electrodes in and I will see the light bulb flash. If I take another acid like acetic acid or weaker acid, you might still see the light bulb flash because it still does produce a tiny amount of ions in solution. Okay, so this brings up what we call the Arrhenius definition of an acid. And according to Arrhenius, an acid is a substance with hydrogen in its formula that dissociates in water. I'm going to put a little star there to yield hydrogen ions. So this was his theory at the time. In a few more lessons, we're going to make modifications to this, and this is not. We can get more general theories that apply to a much broader range of situations than this, but this is kind of what he thought about at the time. And remember, he used the word dissociates. He didn't know yet about ionization, or he didn't at least write down the word ionization. So that's why I'm saying dissociates, but in reality it's actually ionizes. Okay. So this is the Arrhenius definition of acids. It's a substance with H in its formula that dissociates into water to yield hydrogen ions. So out of this we can think of a variety of different acids now that we can recognize from their formula. And you might remember that acids all tend to have hydrogen, a very obvious hydrogen right at the beginning of the formula. And that's how we tell it's an acid. So here's one here. This is what we'd call nitric acid. Or there's also sulfuric acid. They all have a hydrogen right at the start. And when these are put in water, these hydrogens dissociate, or they ionize with the water. So they yield hydrogen ions in the water. Okay, so that's an Arrhenius definition of acids. They'll have a hydrogen in the formula, and they dissociate in water to yield hydrogen ions. Okay, so how does it work with a base? Well, it's very similar. If I take a conductivity apparatus and stick it inside a basic solution like sodium hydroxide, we get the conduction of electricity. So we should expect that light bulb to flash. And that's because there's the production of ions in solution. So what happens here? Well, I'm getting the dissociation of sodium hydroxide into sodium ions and hydroxide ions. And once again, sodium ions and hydroxide ions conduct electricity. This is, remember, a dissociation. This is not an ionization because we start with an ionic compound. It dissolves, the ions dissociate, and we get the conduction of electricity. So this led Arrhenius. This led to the Arrhenius definition. Make sure I spell it correctly. The Arrhenius definition of bases, which is that a base is a substance with OH, with hydroxide in its formula, that dissociates in water to to yield hydroxide ions. I'll put aqueous there. I should do the same with hydrogen. Okay, so a Arrhenius definition of a base is a substance with hydroxide in its formula that dissociates in water to yield hydroxide ions. So what would be some examples of an Arrhenius base? Well, they all will have hydroxide in their formula. So this would be, we already saw, sodium hydroxide, but we could have potassium hydroxide. We could have barium hydroxide. Wasn't watching what I was doing there. Should be a 2 outside the brackets. I don't think I've ever made that mistake before, but when you're recording, you don't know what you're doing all the time. So anyway, so you should have brackets around OH and then a 2 outside. Same thing here, calcium hydroxide. These all have hydroxide in the formula. And there you go, okay? So acids will have a hydrogen somewhere in their formula, and bases will have a hydroxide somewhere in their formula, according to the Arrhenius definition. What we're going to do in the next few lessons is I'm going to broaden this definition. In the next video, I'm going to point out some limitations to this theory. It doesn't quite explain the acidic and basic properties of a few different substances. So this is a very common thing that happens in science. We often find exceptions to rules, and we need to make a theory more general in order to explain the new data. So that's it for this video. Once again, this is the Arrhenius theory of acids and bases. This is a theoretical explanation as to what an acid and a base is that kind of helps explain the conductivity we notice here. It doesn't quite yet explain, pH and litmus paper turning blue or red, but we're going to get to that shortly. All right, see you in the next video.